A linear regression. So earlier we have talked about classification, where your target variable is a categorical variable. In regression, the target variable is continuous. So we will be predicting the value of a variable based on the values of the variables on which it is dependent. Consider I have a variable x and I have a variable y, such that the value of y depends on the value of x. That is, when x changes, y also changes. So in this case, x is called an independent variable and y is called a dependent variable. So linear regression attempts to identify the relation between x and y in terms of an equation, so that this equation can be used to predict y for future x values. That is the summary of linear regression. Now look at this picture. This is how a linear regression works. Say I have a substantial data of x values plotted against corresponding y values. What we do now is we attempt to plot a straight line through these points. The equation of the line takes the form y equal to b0 plus b1x. When there are many independent variables, the equation takes the form y equal to b0 plus b1x1 plus b2x2, etc. Where b1, b2, etc. are called regression coefficients. Does this equation look familiar? It should actually, because it's the equation of a straight line which you would have studied in your school days as y equal to mx plus c. It's the same equation which we are using here for linear regression. So based on the data we have, we plot a straight line and identify the coefficients b0, b1, etc. So when a new value of x comes in, we can predict the value of y using the equation we have just developed. That is how this method is used for prediction. Now to summarize, linear regression is an approach to modeling the relationship between a continuous dependent variable and one or more independent variables. Next, the model assumes linear relationship between input variables and output variable. So that is why it is called a linear regression. Some nonlinear regression problems also may be moved to linear domain by suitable transformation of the model formulation. For example, doing a log transformation of the input or output, or taking the square or square roots of the input or output can transform a nonlinear equation to a linear equation. So we shall see some examples of these cases later. These are my applications of linear regression. Say I know the age, medical history, body weight, blood pressure of a patient. I can predict how much would his treatment cost. Based on the academic performance, prior work experience, age, communication skills, etc., I can predict the salary of a graduate. Based on price, promotion expense, competitor price, etc., I can predict the market share of a product. Depending on the locality, price, carpet area, amenities, etc., I can predict the price of a house. So these are some of the applications in various domains. We'll move on. So there are 5 generic steps involved in building a multiple linear regression model. The first one, data collection. In this step, you identify all your independent variables that affect the dependent variable. Data exploration and pre-processing. We do some initial exploration. So, and first we handle missing data. You would have seen it earlier, right? So, what you do is you could either take the average of the values in the column and do the imputation, or you can probably take the median in case the range of data is very high. You could check out the further techniques we discussed during classification for imputation. The next point, we check if all x are correlated with y. So you remember correlation, I hope. So what we do is we check the correlation of each of the independent variables with a dependent variable. If there is a very low correlation, it means that particular variable will not affect the dependent variable and hence it can be dropped from the model building. Then what you do is you check the correlation of each of the independent variables among themselves. If there is a high correlation between any two independent variables, you will have to drop one, else it will distort the coefficients. So this property is called a multicollinearity. Next step in pre-processing is derive new variables if necessary. So you can compute new variables from the existing variables if needed. Take a case where there are two input variables and one output variable. What you are interested in is the impact of the ratio of the two input variables on the output variable. So you are not interested in the input variables as such. It is the ratio of the input variables whose impact on the output variable you are interested. So what you do is you compute the ratio and have it as a separate field. You probably drop the input variables from the model building if you want. So the next one, categorical variables to be converted to dummy variables. So keep in mind that unlike a decision tree or a random forest, linear regression cannot handle categorical variables. Both input and output variables here need to be continuous or numeric variables, since we are dealing with a mathematical relationship between the variables. So we must convert the categorical variables to numeric using a technique called dummy coding, which we'll see while doing the hands-on. The next step, you're going to train the model. Training the model meaning you're going to estimate the regression coefficients B0, B1, B2, etc. So the method followed to estimate this regression coefficient is called ordinary least squares method. We'll see what is this shortly. The next steps would be evaluating the model performance and then improving the model performance. A couple of techniques to improve the model performance like usage of interaction variables, addition of nonlinear relationships, etc. We'll see more of these in detail in the next video.